Hello, calculus students and seekers of truth. Welcome to the video example on working with a particle moving in two-dimensional space, except this time we are given the velocity to start with, the velocity vector, okay? Not anything about its position. So the vector, or the velocity of a moving particle at time t, is given by the vector t cubed minus 4t and t. When t equals 1, the particle is at 0, 1/2. So we should write out just a little bit of what this means. So I'm going to say that let x of t be the horizontal position, or the x position. Y of t will be the vertical position, or the y coordinate. And we know that x of 1, in other words, when time is equal to 1, x is equal to 0. And we also know that when time is equal to 1, y is equal to 1/2. So y of 1 is equal to 1/2. So we know a little bit about this, and we're given some yet additional information. This stuff right here, the velocity vector. Now remember that velocity is the derivative of position, so that means that x prime is equal to t cubed minus 4t, and that y prime is equal to t. And there's quite a bit of information here that's given to us, wrapped up in two neat little sentences, and we should be able to solve the rest of these problems. So A, find the position of the particle at any time t. So to solve for part A, I am going to figure out what is the horizontal position and what is the vertical position at any given time. So I know that x of t must be the antiderivative of x prime with respect to t. So this is the antiderivative of t cubed plus t dt, which is 1/4 t to the 4th plus, what did I write, minus t? What did I write that? This should be minus 4t. Okay, minus 4t. Wrote it correct up here, got it a little bit confused down here. So this should be minus antiderivative of 4t is, of course, 2t squared plus some constant. Now, in order just to solve that constant, we have to use the initial condition, namely that when t is equal to 1, x is equal to 0. So 0 for x, 1 in for t. And solving for c, we get that 7/4, or 3.75, is equal to c, okay, for the x position. For the y position, we do the exact same thing except for the other equation. So we know that y prime, or y of t, is the antiderivative of y prime dt. So this is the antiderivative of t dt, which is equal to 1/2 t squared plus a constant. Using the initial condition, when t is equal to 1, y is equal to 1/2. So from this work right here, we can see that c must be equal to 0 for the y position. So that means the position of the particle here, the x position, can be given by 1/4 t to the 4th minus 2t squared plus 7/4. The y position is 1/2 t squared plus c, but c is simply 0. So that sums up part A. Now let's keep going. Part B, find the position of the particle at time equals 2. Well, this is pretty straightforward because we've already solved part A. Okay? So for B, what we're looking for here is x of 2, y of 2. Okay? That's the position. That's the coordinate on the coordinate plane. So if we were to take 2 and substitute in here for t, 2 to the 4th is 16 divided by 4 is 4 minus 2 times 2 squared, so that's 8. 4 minus 8 is negative 4 plus 1.75. This gives me 2.25 or 9/4 for the x position. For the y position, if we were to take 2 and substitute it into here, 2 squared is 4 times a half is 2. So that's this right here, 9/4, and, or I'm sorry, this should be negative 9/4. My arithmetic got away from me there for a little bit. Negative 9/4, 2, is the position of the particle at time 2. Now, what I'm going to do here is pose a little bit of a challenge, and this is a challenge for you to really help you develop your problem-solving skills. Answer part B without using this. Can you answer part B without using this at all? Okay, so you should really take this on your own. It's an incredibly useful skill to have, to be able to solve this type of problem without actually figuring out the position function. Okay. But I'll leave it there for you to work on. I'm actually going to continue this problem and answer parts C and D. Okay, so part C asks of us, find the equation of the line tangent to the motion of the particle at t equals 2. So for your convenience and just to help you visualize, I've graphed this right here in my calculator. And we can see that when t is equal to 2, the point is right there. Okay. Now what we want to do is find what is the equation of that line, or the line that's tangent to the motion. So very rough sketch here. So like right about here is where t is equal to 2, and we want to know what is the equation of that line. Okay. What's the equation of this line right here? Well, to find the equation, we need a slope and a point. The slope will be provided to us by calculating dy dx. Now, dy dx we already know is really equal to dy dt divided by dx dt when t is equal to 2. Well, now let's think about this. What's dy dt? Well, the derivative of y with respect to t. And that was actually given to us at the very beginning. Dy dt is equal to t. Remember that we were given the velocity. So when we go to find position, we take the antiderivative of velocity, and now we're going back and we're saying, well, what's the derivative of the position? Well, of course, it's back here to the velocity. So dy dx is equal to dy dt, which is just t, over dx dt, which is t cubed minus 4t. So dy dx when t is equal to 2, and that's what the question asks here, when time is equal to 2 is equal to 2 over 2 cubed minus 4 times 2. So in the bottom I get 8 minus 8. So this is undefined. Okay. In the denominator here I get 2 to the third, which is 8, minus 8, which is undefined. So that means my picture here is a little bit wrong. This point right here isn't really slanted like that. It's actually right here and it's perfectly vertical. Okay. Now, we know that the equation of a vertical line is like x equals something, so we just need to know the x-coordinate of this point. But we already have the x-coordinate of this point in some ways. It's negative 9/4 from what we had before. When time is equal to 2, x is equal to negative 9/4. So this question turns out to be a little bit easier, a little bit simpler than we originally anticipated, which is always wonderful, that the equation of the tangent line to the motion right here is really x equals negative 9/4, because that tangent line is vertical. Okay, and this point right here is actually a critical point. It's a moment when the particle goes from this motion to this motion right here. And now we have this question: how far did the particle travel during the interval 1 to 5? T equals 1 to t equals 5. Well, remember this is really how far did the particle travel. So this is really the arc length of the position function. The arc length of the position functions. Okay. Well, we know then to calculate arc length, we're going to integrate between 1 and 5. And this is going to be the square root of dx dt squared plus dy dt squared, okay, dt. But what is dx dt and dy dt? Well, dx dt is the derivative of x with respect to t. In other words, it's x prime, which was given to us already at the beginning. Same for dy dt. It's the derivative, because we're taking the derivative of position, which is nothing more than the velocity, which is equal to t. So now we can do this calculation. Dx dt quantity squared is equal to t cubed minus 4t quantity squared plus dy dt, or y prime squared, is just t squared, integrated with respect to t between 1 and 5. And like before, I'm going to let my calculator work on this one instead of me have to work out all the nasty algebra. So typing this into a calculator, I get an answer of approximately 114.136. Okay. There's no units here, so we don't have to give any of the units. So we have completed another example here where we are working with particle motion, but instead of being given the position functions, we're given the velocity vector functions, and we're asked to find some information about the problem. As always, if you have a hard time, ask for help. Thank you for watching. Have a wonderful day, and work really hard on solving this little challenge here. It's not too difficult. It's definitely within your reach.